Well, I hope things are going well for you in the class. You just had a chance to take the midterm, and hopefully that went well for you. Again, through the midterm, we were learning how to actually influence memory locations, and that everything in memory is basically just bits, and you can point to it with whatever kind of a thing you want to. I think that's an important objective of the class. The other objective is to remove some of the magic about how a processor works. And so you've had a chance to look at AND gates and OR gates, and maybe at some point to gain the insight that if you had to, there's nothing magic here. You could put together hardware that would actually execute a instruction. And so now we're going to talk a little bit about a simple assembly language, and I think just basically how do we, what does our C code turn into after it's compiled? So hopefully I thought this would be good to have a little video. I'm going to go through this fast. Again, make sure that you take advantage of the slides, which are always available. If you take a look at the reading and resources, so you'll notice that there's always going to be, you can watch a video lecture from the class, or you can actually look at these slides. So I was going to go through a few slides. I know this is kind of boring, but I wanted to just hit some high points, and hopefully that'll give you an idea of where to go next. So let's go ahead and talk about this, but we're going to have you right now use this assembly language called Y86-64. And again, assembly is human readable machine code. So first we will compile your C code into assembly code, and then you're going to assemble that assembly code into machine code, which are just the zeros and ones that the computer can execute. So we've talked about this before, that you've got this memory, which is just zeros and ones. Your central processing unit then becomes the unit that will access memory and actually make things happen. And really the programmer's state is going to be all of memory. It's going to be your registers, and we have a very small number of registers in this Y86. Your program counter, which is where are you actually executing from, and then condition codes. So whenever we do something, an instruction, we can tell was the result 0 or signed or overflow. And then that's kind of the information that you actually have. So we're going to then take a look at this, and you will become real familiar with this in the next little while. So again, this Y86-64 is simple. Later we'll look at X86-64, which is running on most of your machines, and that's the Intel architecture. Okay, a few things to think about. First of all, this Y86 is going to mostly do things with quad words, but you could also think of accessing a byte or a word, which is 16 bits, a double word, which is 32, or a 64-bit word. And so when we get to the X86, we will see some of these others, but for now, Y86 just does quad words, so it makes it simpler. And so here's the instructions you can see. Halt is stop the process, or you could not do anything. You can do a move or move queue to move from register to register, a immediate to a register to memory, that saves it out in memory. And then you can do conditional moves depending upon those status bits that we talked about before. Also, your arithmetic logic unit, or ALU, you can add things, subtract, and XOR. And again, when we look at the X86, we'll have some more ALU operations. And then you can do a jump based on those status registers as well. Whenever we actually run a program, we're going to push things onto the stack. For example, when we call a function, and we'll pop them off when we return from the function. So that's not very many different operations. There's the move operations. Again, you're going to have a source and destination address. When you do ALU things, we're going to add the first operand to the second, and then put the sum into that second register. So this is kind of tedious if you think of, you don't have any variables, you just have these registers, and then you can save things out to memory. Here's the condition codes we talked about before, and these condition instructions then can be used to actually do jumps based on what those condition codes are. So here's some examples. You can do copy a value if the corresponding condition is satisfied. So cmove not equal, cmove less than equal, greater and greater than or equal. So anyway, kind of some things to think about. Also, we have conditional jumps. So these are in essence if statements. So you'll use these to build if statements and while statements. And you can also have stack instructions. Excuse me. And so what the example that they kind of went through in these slides is write a sequence of instructions that will compute hex 200 plus hex 24 and put the result in this RAX register. Okay, so if we wanted to do that, first we're going to have to move this hex value of 200 into RAX. We're going to move the value of 24 into RCX. Again, if we take a look at our registers, here's RAX. And we also have the opportunity to move another one into RCX. We're going to add those two together and put the result back in RAX, which is what we said we wanted to do. And so if we take a look at the execution of this, we'll first move a 200 into RAX. There it goes. And the simulator will let you look at these. We're then going to move a 24 into RCX. There's the 24. We're then going to add the RCX and RAX, put the result in RAX. There it is, 224. It worked. So now we're going to say, let's look at the simulator. And this is why I wanted to do a little video, because this can be a little bit daunting when you first get started. So we're going to actually go to this online simulator here. I'm sorry, it's not working out exactly like I anticipated. And then we're going to actually run that. So let's go ahead and do that. Here's the simulator. And the first thing you can kind of look at, execution is going to begin at address 0. So we'll say this is address 0. And first of all, we're going to say the stack belongs at position 200. By the way, this could be anything, but you'll notice that over here we have a bunch of different addresses. 200 is kind of someplace in the middle here. So we're going to go ahead and we'll start pushing things on the stack. And this region will be for our stack. Usually memory values lower. We're going to start out by putting our code here, and then we'll have some data that's in the next positions. Okay, so here we're going to say move this stack into my stack pointer, and then we're going to call main, which will push the address of this next instruction onto the stack, transfer execution down here to main, and then it will execute that and then eventually do a return, which will pop this address off of the stack and do this halt instruction. Okay, so now we're going to kind of go back here. we're going to say, let's see, what did we actually want to do? We wanted to do this move 200 into RAX. And so now I'm going to go ahead and put that into my main code here. And then I wanted to grab this 24 and put it in RCX. And then I wanted to, I'll put that in here in main 2. And then I wanted to grab add CX to AX. And now I have actually done that correctly. So if I do that, I can then say, okay, let's now assemble this code. And here you can see this is actually the object code, right? This is the assembly code. So you can imagine, you know how you're always writing main, a function called main? That's so that you can actually call main and it's going to do the business of what you want with your function. So in this particular case, we can now single step through this. Notice here we have all of our state. Here's our registers, here's our flags, our status, and our memory. So you can see all of it as you go. And so now I can go ahead and step. So I'm going to move the 200. So here we said that position 200 is going to be my stack. So I move 200 into RSP. And so now you can see here's my register SP, and it's got a 200 into it. And it shows over here that it actually put that in there. And this is one of those 8-byte values. And so now we're going to single step again. Okay, we went into main. So this is the call main. So now our program counter got modified. So now we are executing down inside of main at this first IR move Q instruction. And our program counter, notice, is now at hex 14. And we actually pushed a 13 onto the stack. That's the address we're going to return to when we're done. Okay, so now we do another single step, and you'll notice that, lo and behold, we now put a 200 into RAX. That's what we expected. We do another step, we put a 24 into RCX. Now we do another step, and we're going to add our CX to RAX. And lo and behold, we have 224 here, which is what we expected. And then notice here my program counter is at hex 2A, but now I'm going to execute a return instruction, which is going to grab the save program counter off of the stack, put it in the program counter. And so when we step here, you'll notice that the program counter was changed to 13, which is the next instruction after the call to main. And now we're just going to execute this halt and halt our processor. So hopefully that gives you an idea of how to use assembler, what this assembly language is like. I'll probably be making a few more videos because this part I think you can use some more help on and help you through the lab. So that should be helpful. We'll see you next time.